glad to explain further or to delve further onto these calibration techniques, but we don't have enough time. We don't have the luxury of time to give you the details on these techniques or these instruments. Okay, so next we have the external calibration, standard calibration. So what are we going to do here is you will plot, or you will plot the different the data that you gather, and you are going to generate a calibration curve using linear least squares methods or regression analysis. So this would somehow give us the data if this particular instrument is well calibrated or not. If this would give us the regression data or the coefficient of determination, which is less than as 1 or 0.999. So there is error, or there are a lot of errors that probably occur during the conduct of the calibration. Okay, so in the external standard, so this is not dependent on the sample and is run separately. And you can generate here you are going to generate the known standard and the measure signals. Okay, so these are the measures that you get from the instruments, and you are going to plot it. To plot those data, for example, you get the absorbance and the concentration. You are going to determine the relationship of the absorbance and the wavelength. Okay, so that is how you are going to generate data out of this particular method, which is the external standard calibration technique. And you are going also to have the linear regression, or those the linearity. You are going to observe also, to take note the linearity of the data, because this will give us the understanding if this particular instrument is calibrated, is well calibrated or not. Okay, so this is the example of a calibration curve. So this includes now the blank, no, or the reference sample. Okay, so it can be a reagent blank, or it could be or ideal blank. Okay, so here the points here. So these are the points, no, of the data that you get from the instruments. Okay, so in this particular example, so say for example, this is in the y-axis, you have here the absorbance, and in the x-axis we have here the concentration of the sample. So this is how you are going to generate your calibration curve, and it must be, as much as possible, it should be the R squared, or the coefficient of determination, must be equal to 1 or 0.9999. Okay, so that we could somehow, the percentage error is it's not quite big, and it could not affect the result if you will run the true test in the instrument. Okay, so here, so let's now have the ultraviolet visible spectroscopy. So as what I have told you, that we are going to focus only on one spectroscopic method, which is the UV Vis spectroscopy. So here we have first the introductory idea or information on UV Vis. So spectroscopy, so this is what I have been telling you, that this is the interaction between light and matter, or the radiation and matter, or the interaction between the light that you that is subjected in the sample. Okay, so spectrochemical method, so this is based on measuring the amount of radiation produced or absorbed by molecular or atomic species of interest. So the largest and most important single group of techniques used in analytical chemistry, providing a wide range of quantitative and qualitative information. So So spectrochemical methods, this is a very important instrumentation specifically for chemical analysis. And group of techniques that relies on the interaction. So it can be atomic or molecular interaction of electromagnetic radiations such as in the NMR. Okay, so it could be absorption or emission of this light. So UV-Vis spectroscopy. So it is an analytical technique that measures the amount of discrete wavelengths of UV or visible light that are absorbed by or transmitted through a sample in comparison to a reference or blank sample. Of course, if you have to run your sample using the UV-Vis, you must always have your reference or blank sample. Blanking is very important in any spectroscopic methods. Okay, so you must have a reference point in order for you to determine if this spectroscopy gives you the accurate and precise data. Okay, so you must have blanking, because blanking would also lead you to the calibration of this particular instrument. If this won't give you accurate or precise data or a linear curve, then the data that you've been collected in the instrument are not they are not valid, or they are not reliable. Okay, so this property is influenced by the sample composition, potentially providing information on what is in the sample and what is the concentration of the sample. So later, we will discuss deeper on UV-Vis spectroscopy. And I have a short demonstration and sample data that I've collected using the virtual laboratory. Okay, because we don't have yet we don't have yet the face-to-face interaction. That's why all that I can give you is the data coming from the virtual laboratory, and later I will present it to you. Okay, so because we are talking on UV-Vis spectroscopy, so you must also take into consideration the electromagnetic spectrum and the location of the visible light and the UV light. Okay, here in the center, you can find the visible region here that is between that is between 380 to 780 nanometers. Okay, so that is in the visible region, but in the UV region here in this area, you have the wavelength of 180 to 380 nanometers. Okay, so in the infrared region, in the near IR, so that is between 0.78. So we are using micrometers because the wavelength of IR is dispersed, is more dispersed than your UV and the visible region. Okay, while in the mid IR, you have that's between 2.5 to 50 micrometers. Okay, so this is the basic electromagnetic information that you need to consider also in the UV-Vis. So next we have the ultraviolet or the visible spectrum. So under the visible region, you have here the colors of light being absorbed and the complementary color that are being transmitted. Okay, so at wavelength of 400 to 435, the color that is being the color of light absorbed is violet, and the color that is being transmitted is between yellow and green. Okay, so and so on. So you have here 435 to 480 that is blue, and the complementary color that is being transmitted in the instrument is yellow. So later we will have the working principles of UV-Vis instrument. Okay. So how does absorption or how does light is being absorbed in the sample? Okay, so we have here this absorption spectroscopy. So we have the incident radiation that is labeled as the P sub 0, or the incident radiation power. So as it enters, or as it enters the sample, so the light that is being transmitted is called as the transmitted radiation. Okay, so later I will also explain to you the application of Beer Lambert Law in UV Vis spectroscopy. Okay, so in the second illustration is the excitation of light, or of the photons, or the electrons of the photons from the ground state to the excited state. So this is the mechanism of the excitation of light. And we have here the resulting spectral display in your figure C. So we can generate a spectrum out of the data that we've entered in the sample compartment. Okay, so this is how absorption spectroscopy works in UV Vis. Okay, so here is the working principle of UV Vis spectrophotometer. So Monish, this is the working principle. So you have here the light source, so it can be a deuterium light or a tungsten bulb. Okay, so those are the light source for UV Vis. So we have here the entry slit, or the lens, or the collimator. So it's basically a glass. Okay, so it is where the light passes through, and then as it reaches the prism, it creates the different colors of your visible region. Okay, and the wavelength selector, so here in the exit slit, will then select what kind of wavelength that could pass through the sample. Okay, so here, as the light, or as the wavelength reaches the sample solution in the sample compartment, so we have here that the two types of radiation. Okay, the first is the incident radiant power, or the P sub O, or the I sub O. That is just the same. So the I sub O is greater than your I sub T, or your transmitted radiant power. Okay, so because, say for example, if your incident radiation power is 100%, so you cannot expect that in the transmitted radiant power, it can also have 100%. No, it's not, because there are the sample solution also could absorb some of the light that passes through it, that passes through the cuvette. Okay, so say for example, if you have 100% as your incident radiant power, and you have 75% only the light that passes through the sample, so you can expect that the 25% of this radiant power, or of this light, is being absorbed in the sample. Okay, and until this transmitted radiant power reaches the detector of the instrument, and it would now display the data. It could be transmittance or absorbance. So in transmittance, the lowest is 0 and the highest is 1. So that's between the value for the transmittance is between 0 and 1, while in the absorbance it could be more than 1. Okay, so that is how the UV Vis spectrophotometer works. Okay, so next we have the application of the Beer Lambert Law. So why is it why do we need to consider the Beer's Law, or the Beer Lambert Law, in the study of UV Vis spectroscopy? Because if you could only get the data value using the transmittance, you could not, or the type of data that you will get from the UV-Vis spectrophotometer, you cannot get the calibration curve, because it will not give you, or it will not display a linear data, but it displays an exponential curve or exponential graph. So it will transmittance, the relationship between transmittance and the concentration. So it is going downward, but in a curve form. Okay, so using the Beer Lambert law, it could correct, or it could give us a precise, and it could give us a clear data on the relationship between the absorbance and the spectrum that we could get from this instrument. Okay, so according to Beer Lambert law, so absorbance is equal to the negative log of transmittance, or it is equal to log of the incident radiant power over the transmitted radiant power, or it could also be presented as absorbance is equal to molar absorptivity times your path length. So the path length, it is the size of your cuvette, or it is the distance that light travels in the sample, and the concentration of the sample, which is represented by C. Okay, so you have here the relationship in this illustration, the relationship of absorbance and transmittance. So these particular data are they have a inverse relationship. So if the absorbance is increased, the transmittance also decrease. If the transmittance increases, the absorbance decreases. Okay, so they have inverse relationship with one another. So as you can see here in this illustration, so here we can really prove that the incident radiant power, so as it passes through the sample, the light that passes through the solution, or the transmitted radiant power, decreases. That's why the P sub 0 is greater than your P, okay, or your P sub T, or I sub T, or I sub O. I sub O or P sub O, they are just the same, or I sub T or I, just I, or P. Okay. So this is the principle, the principle behind the application, or why do we need to apply Beer Lambert law in the study of UV-Vis spectroscopy, or in the UV-Vis instrumentation. Okay, so absorbance and transmittance are unitless if C is in mole per liter and B is in centimeter. Then your molar absorptivity, or it is represented in epsilon, is liter over mole times your centimeter. Okay, so that's why absorbance and transmittance are unitless, because these units will be canceled if you're going to calculate the absorbance and transmittance using the formula. So in order to minimize the effect of light losses from reflection, the procedure followed in UV-Vis spectrophotometry is to measure the incident radiant power with a reference blank or pure solvent in the light path, and then measure your transmitted radiant power under the same conditions. So cuvettes should be optically matched if using these two. Okay, and they must be clean, free from scratches, lint, fingerprints, and etc. That's why in holding your cuvette, there are two phases of your cuvette: the rough phase and the shiny phase. So you do not hold it in the shiny surface, okay, but you need to hold it in the rough surface, because in the shiny, it is where the light passes through the sample. Okay, so in dealing with cuvettes, so in order for the instrument will give you inaccurate data, so you need to handle it, okay, or you need to handle the cuvette, so in the rough surface only, not in the shiny surface of your cuvette. Okay, so because it could affect the result of it could affect the data that that the instrument will produce in the long run. Okay, so next we have the sample problem. So for example, if you have here, if you will calculate the absorbance and the molar absorptivity of this particular solution of, for example, here we have a 7.25 times 10 raised to the -5 molar solution of potassium permanganate. It has a transmittance of 44.1%. So you need to convert that one into decimal points. That is 0.441. And it's when measured in a 2.10 centimeter cell. Okay, so that is your cuvette at a wavelength of 525 nanometers. So this is your lambda maxima. So first, you're going to calculate the absorbance of the solution. And the second is the molar absorptivity of potassium permanganate. Okay, so here in your solution A, we have here the formula for absorbance, that is negative log of the transmittance. Okay, so the negative log of transmittance, so that is 0.356. So this is now your absorbance. And for your molar absorptivity, using the formula, A is equal to epsilon times B times C. So our absorbance is equal to molar absorptivity times your path length and times the concentration. So you have here if you are going to rearrange the formula, or you are going to derive the formula for molar absorptivity, you could have here the rearranged formula of epsilon is equal to absorbance over or divided by your path length times the concentration. Okay, so that is equal to 2.34 times 10 raised to the 3 liter per molar times centimeter. Okay, or this is just basically measured. You are going to convert this into molar, or big letter M, times centimeter. So in order for you to get more simplified result. Okay, so because liter per mole, that is the molarity of the solution. That refers to the molarity of the solution. Okay, so I have here a virtual lab application and demonstration entitled Determination of Molar Absorptivity of Para-Nitrophenol, or the PNF. Okay, so using this link, sir, can I can also share this link to you, so that you could also somehow open the virtual lab. Would that be okay to you?
Okay, yeah. I think we can to open the link. All the participants can join, right?
Yes, sir. So that you could be able to see also the virtual laboratory.
Okay, quite interesting. Okay, to all participants, please open the link which already appears in the chat room.
Okay, so you have here, sir, excuse me, sir, can you see now my the virtual lab?
Yeah, I just in loading here.
Participants, can you now see the virtual lab?
No, we can't see the virtual lab, sir.
Yeah.
Okay, what's the problem?
It is still not yet appeared on the screen.
Okay, now it's appear now. The virtual lab. Isn't it? To all participants?
Now, can you see now the virtual lab?
Yes,
Yeah.
we can.
Yeah.
Mister.
Okay, so this is the virtual live, the virtual lab. So for UV Vis spectroscopy. So you have here the instrument that is used to measure the absorbance or the transmittance of, of the sample. So you have here, for example, if firstly, the first data or the first thing that you need to get from from this instrument is the spectrum. So you need to get the lambda maxima in order for you to set the lambda max, okay, for the sample that you will use, no? In order for you to get the absorbance of each sample using the lambda maxima. Okay, say for example, first you must open the instrument. Then before you will run each sample solution, you must see to it that you perform first blanking. So you must have your blank solution. You have here water as your blank solution. You must see to it that the absorbance is 0. Okay, so if the absorbance is greater than is greater than 0, then you must click the auto 0, or you must select the button the button that contains here A is equal to O, or it will then guide you, or it will then display an absorbance that is equal to 0. Okay, say for example, you have here, so in the first cuvette, you pour 3 ml water. So 3 ml. Then, when you are going to run the blank solution, so water lang, you can only use water here because this is just the available blank solution in the virtual lab. So then you transfer the cuvette in the sample compartment. Then, as you can observe, that the absorbance is negative 0.098, and in order to calibrate the instrument, in order for you to get the data, the desired data for this particular instrument, so you must set the absorbance for your blank solution to 0. Okay, so you must click auto 0. So now you can have you have now here the absorbance value for your blank solution, which is equal to 0. The absorbance is equal to 0. Okay. Next is, you also need to get the spectrum of the para-nitrophenol or your PNF solution. So next is, you are going to pull out your blank solution and then replace it with your PNF solution. Okay, but your PNF solution must be concentrated, because we need to determine the lambda maxima of the PNF solution. Okay, so we are going to use the second cuvette. So that's still 3 ml. Okay, do not worry, because the working principle in this virtual laboratory is somewhat similar to the actual instrument that we used for chemical analysis. Okay, so the working principle is just the same. So as you can see here, the absorbance is 0.015, but it could we cannot or we can neglect first the absorbance because what we are trying to get first is the spectrum, okay, or the lambda maxima. So we now run the instrument. Okay, so we could now somehow determine that the lambda maxima is near 400 nanometers, but actually it is quite, it's not 400, it's not exact 400 nanometers, but the lambda maxima for this of the PNF solution is at 405 nanometers. And we will use that lambda maxima in order to determine the absorbance reading of each sample. Okay, so we could now have the lambda maxima of the PNF solution, and then okay. So the next thing that you need to do is you are going to set the standard solutions that you will use in the instrument. Okay, so here in your first cuvette, we have, for example, 2:1. So 1 ml PNF, 1 ml PNF, okay, and 2 ml water. Okay, so next is in the second cuvette, 1:1, the ratio of your PNF solution and your water is 1:1. So we have here, for example, 1 ml water and 1 ml PNF solution. But before you are going to run each sample, you must see to it that you will perform first the blanking. Okay, for 1:1, 1 ml PNF and 1 ml water. Okay. So for the third cuvette, so you could also use the third cuvette for your blanks, for the blank reagent, for the blank solution. Okay, so as you could see, the spectral display is at 800 nanometers. So you will reset this to 405 nanometers as your lambda maxima. Okay, because you will only use lambda max for each of the sample at 405 nanometers. Okay, so everything is set. Now transfer the third cuvette to the sample compartment. So you first perform blanking. So here you could you can have the absorbance of negative 0.001. So you must set it to 0. Okay, then transfer the first solution in the first cuvette. So this is your first standard solution. So that is 2:1. So 2 ml water and 1 is your PNF solution. So you have here the absorbance reading for the 2:1 ratio of water and the PNF solution. You have here the absorbance of 0.537. Okay, so that is the absorbance of the first solution that you run in the in the Vis Spectrophotometer. And do not forget to record also the spectrum of this sample, okay, because you will also need the spectrum in order to better understand your data. Okay, so this is now the spectrum for your first standard solution, 2:1 ratio, 2 ml water and 1 ml PNF solution. That is the concentration of your PNF solution here is 80 micromolar. Okay, so the lambda maxima of your PNF solution is at 405 nanometers at 0.5 something absorbance. Okay, so that is the spectral display of your first solution. Okay, so we're gonna have now the second solution. I know. Okay, the spectrum is not set to 405 nanometers. So 405 nanometers.
So, Mr. Ecle, we only have 5 minutes left, Mr.
Yes, sir. Okay, so you have here the absorbance reading of 0.815 for your second solution. That's how you are going to do or to measure the sample, no? To determine the measurements or the absorbance reading, and you can also have the transmittance or the transmittance reading using the Vis Spectrophotometer. So I have here the sample data that I've gathered, that I've collected from the virtual laboratory. Okay, so here, using these sample standard solutions, I have the first standard solution is the blank solution. The second, third, fourth, and fifth solutions are the solutions containing the para-nitrophenol and water, the concentrations of with corresponding concentrations of the PNF, which is at 80 micromolars. Okay, and here are the spectral display, okay, in the gathered data. So these are the different spectral displays and the calibration curve. So as you can see, the calibration curve, so you can hear that the coefficient of determination is equal to 0.9999. So there is only less percentage of error that is happened during the calibration of the instrument. Okay, so in calculating the molar absorptivity, so you will use the line equation y is equal to mx plus b, and that is similar to the Beer's law. Okay, so in calculating the molar absorptivity, we could find that the molar absorptivity of the PNF solution is equal to 2.22 molar times centimeter. Okay. So this is an example of data measurements and calibration using the Vis Spectrophotometer. So I have here one, but we don't have now the time to discuss this virtual lab. So this is actually UV visible spectrophotometric determination of the concentration of two dyes in a mixed solution. So these are the sample data. You have here the spectral display, the corresponding spectral display based on the different wavelength, and of course the calibration curve of the red dye and the blue dye. You have here the coefficient of determination is equal to 1, so that's perfect 1. So it means to say that um, the instrument is well calibrated. Okay, and the sample calculations. So I guess that's all for my presentation this afternoon, sir.
Okay, thank you very much, Mr. Ecle. This is so interesting, yeah. Okay, we also have some related course, yeah, about calibration technique, yeah. This is a similar what have you talking about, yeah. This is how we calibrate one instrument. I think to compare the data to the standard
Yes, sir.
measure, and also we also have a calibration group like that. So I think it's very interesting. And also when we applied in the chemical analysis, okay, the chemical analysis is very important recently, yeah, since we are in engineering. So we also working as the industrial engineering who can produce the waste or something else which is thrown to the environment like that. Okay, we back to the next step is question and answer. There is several questions, sir. I think this is very interesting. Why our students so excited to ask you a question like that?
Yes, sir.
Okay, and the first one from Octavian Zulkifli. How to read uncertainty 95% certificate calibration of spectroscopy UV visible?
Sir, again, sir.
Okay, I would like to read again. How to read uncertainty 95% certificate calibration of spectro UV visible.
Excuse me, sir. I really don't understand, sir.
Okay, I think the
I really
question
don't
is about more or less like how to. Okay, I think I would like to ask, yeah, better to speak with the Octavian Zulfiki. Are you there, Octavian? Octavian? Okay, I think she or he means about the how
can I
to read
read, sir, the
uncertainty.
question? Can I read, sir, the question?
Okay,
So
okay.
that I could better understand what
Yeah,
is trying to,
I already
how
type
to
it.
read uncertainty.
How to read, right?
Okay, so the uncertainty, so the uncertainty 95% certification calibration, how to read uncertainty 95% certificate calibration of spectro UVV. So I have presented earlier the standard operating procedure, or the here, the acceptance criteria and the corresponding uncertainties. So it means to say that, for example, here in the first standard solution, 20 milligrams per liter, you get the corresponding absorbance values, and you have also the uncertainty that is equal to 0.0034. Okay, so this is, I think, sir, this is standard uncertainty values in measuring the absorbance readings for UV vis spectroscopy.
Okay. Thank you, Mr. Ecle, for the answer. I think Octavian, there is any feedback for them? Octavian? Okay, I think she has or she or he has not good in internet like that. Okay, we next question. We have the next question from Deva. She has a two question. Okay, in the first one, can we use it to analyze hydrocarbon composition?
Hydrocarbon, yes, sir. Yes.
Yes. Okay.
Yes, sir.
We can, is yeah. Or
Yes,
is there
sir.
any limitation on what properties we can analyze?
Sir, yes, sir. Again.
Or is there any limitation on what properties we can analyze?
Yes, sir. There are limitations also for this particular spectroscopic method. Say, for example, I guess that the solution must be in a liquid form. So you cannot just simply put all of the samples that you want to determine using UV spectroscopy, because there are also there are also things that we need to consider in running in running the sample solution, or whether it is known or unknown substance. It should be in a liquid form. So not all substances that are available in your area can be read in the UV vis.
Okay.
But it must be diluted, or it must be diluted first, for example, in a solvent or and others.
Okay, thank you, Mr. Ego. But there is another question also from same person from Deva also. Is HCDP or hydrocarbon dew point also one of the application from the spectroscopic method?
Again, sir?
Is hydrocarbon dew point also one of the application from the spectroscopic method?
Sir, you are a bit choppy, sir. I cannot really understand
okay, maybe I think
what your question, sir.
Trouble internet connection also here. I'm sorry. I would like to here. Okay, this is
so for the composition analysis, so it's better to use infrared rather than UV vis, because infrared spectroscopy is more appropriate in determining what kind of chemical composition that can be found in a particular molecule or in a particular sample, sir. UV vis, you can the main purpose, or the data that we can get in UV visible spectroscopy are basically absorbance data and transmittance data only. But as to the composition or the structural elucidation of these molecules, or these hydrocarbons, is more on infrared or NMR, or nuclear magnetic resonance spectroscopy.
okay. So there is the second question also there. Is HCDP like that in the bottom of my chat room? Can you see, sir? Hydrocarbon dew point also one of the application from the spectroscopic method.
I am not familiar, sir. Honestly, I am not still familiar with the hydrocarbon dew point. Can you, whoever questions this, can you further elaborate what is this HCDP?
Please.
Sir, excuse me, sir. I cannot understand
we
your
have a
sir.
question. Are you still there? Hello? Okay.
Hello, sir.
Okay, I have a bad internet connection also, yeah. I'm sorry. Could you hear my voice clearly? Check. Hello? Hello, Mr. Ecle? Could you hear my voice?
Yes, sir. Yes, sir. Yes,
okay,
sir.
good. Okay, I would like to invite Deva. Deva, are you still there? Could you explain more detail about your question? Okay, Deva. Please welcome, Deva.
Hello, can you hear me, sir?
Yes, yes, we can hear.
Okay. Well, my question is, hydrocarbon dew point is like one of the analyzer that we use to measure the dew point of a hydrocarbon. So we use it. We also use it in the custodian place. Yeah. So I wonder if it's one of the application from the spectroscopic method, say, because it's used like a photo sensor. Yeah.
Okay.
Should I repeat what I just said? Okay.
Okay. Maybe this HCDP can be applied using other spectroscopic method, but not UVVs.
Okay. Thank you, sir. I appreciate the answer.
Okay, do you have any question
Appreciate
again,
the
Deva?
answer.
Do you have
No,
still
I
have
think
any
that's
question?
enough.
Okay.
No, I think that's enough.
Oh, that's enough. Okay, thank you, Deva.
Thank you.
Okay, for the next one is from Nabila Chandra.
Thank
She
you.
has two questions here. In the first one, what are the common error occur during measurement process using UV visible spectroscopy?
Okay, there are a lot of errors. It could be in a matrix error or systematic or random errors that could probably happen in the conduct, specifically during the calibration of the UV visible spectroscopy. Say, for example, as what I have been telling you a while ago, if you do not handle the cuvette properly, so there will be an error on the absorbance reading or on the transmittance reading because it could affect the result of the absorbance. Okay, it could also affect the transmission of light from your from the instrument. Okay, so and of course random errors and the other errors that could probably happen are also called as systematic errors. So yes, sir.
Okay, thank you. Follow up by the second question, sir. Considering there are few type of chemical instrument calibration, what
Yes,
is the method of calibration that most likely used in calibrate the UV visible instrument?
Okay. So in UV visible spectroscopy or in the UV visible spectrophotometer, um, um, we use the direct comparison, which is that using the standard operating procedure where you compare the standard measures with the data that you've collected using during the calibration. And the second one is external calibration method, as what I have telling you, using the calibration curve or using the least square method, sir. Or the
Okay.
regression analysis.
Okay, thank you, sir. Might be Nabila Chandra have a comment about the answer from Mr. Ecle. I would like to invite Nabila Chandra.
Hi,
This is enough.
sir.
Yeah.
Audible? Am I audible?
Yeah, yeah, I can hear your voice.
Yeah. I think that's enough for the questions. Thank you so much for answering these questions. I really appreciate that. And I think it's clear for me. The answers is entirely answered my question. So thank you. Thank you so much, sir.
Thank you. Thank you so much, ma'am.
Okay, thank you, Miss Nabila, for the question. Okay, next question, sir. All right, this is from Tioku Zahrian Azril Alas. Hello, Mr. Ecle. I want to ask you how important is the measurement science and how will it work in the 5.0 industrial revolution in the future? Thank you.
Sir, again, sir, can you
Okay.
repeat po?
Okay.
Can you repeat, please?
How important is this measurement science and how will it work in the 5.0 industrial revolution in the future?
Yes, UV visible spectroscopy. There are a lot of applications on this particular instrument, specifically in drug or medical industries and food industries, because these particular industries or these particular establishments should see to it that there should be a quality control of the concentrations that they use in making food products or in making these particular products. So that's why, for example, if the absorbance reading will not meet the standard absorbance reading set by the company, so there is a mistake during the conduct there is a, for example, there is for example, the concentration coffee, for example, the food product is coffee, then there is then the absorbance reading is not similar to the standard set by the company. So there might be errors, or there might be, for example, the concentration is being increased. Diba? As you can observe in the Beer's law, the absorbance of the sample must is equal to the molar absorptivity, the path length, and the concentration. So if you are going to increase the concentration of this particular molecule, then the absorbance reading will also increase.
Okay, that's quite a good answer. Maybe any feedback from Teoku from the answer from Mr. Ecle? Any feedback?
I think it's enough, sir.
Enough. Okay, this is enough.
Yes.
Okay, thank you, Mr. Ecle, from the question. Teoku Zarian? This is enough, yeah?
Yes, enough, sir.
Enough, okay. Yeah, okay. I think my question here is already finished. I would like to invite a participant who have any question, just raise your hand, and then I would like to give you opportunity to ask directly to Mr. Ecle. Please welcome. Any question? Okay, sir. I think I have one question here about it. Since this is for the spectroscopy, we have so much project in during the industrial, especially in water treatment. Also, you already explained it how to measure, how to detect the mercury for the water treatment like that. So we have a project like COD and DOD, like chemical oxide demand or biological oxide demand. How to analyze this using UV visible? Is it okay?
It's more appropriate, sir, if we could use AAS or atomic absorption spectroscopy, because this particular spectroscopic instrument is more appropriate in determining heavy metals, sir.
Okay, this is very, very useful. Yeah. Wow.
Yes, sir. Because each spectroscopic instrument, sir, they have different also functions. They have different functionality, and they have different also data that it depends on what data that that the researcher wants to have on his or her research.
Okay, good. So, what is your project in your PhD there?
Sir?
What is your project for your PhD right now?
Actually, sir, we have in our department, because I am education, not really in pure chemistry. I am not really into pure chemistry, but I am only we have chemistry subjects. We have a lot of chemistry subjects, but our focus or our research must only be focused on chemistry education, but not on pure chemistry.
Okay, chemistry. Especially, what is the difference with pure chemistry and chemistry education in your major, especially?
We in chemistry in education, we are only using the information, or we are only using we are only applying the principles behind chemistry, and we are going to arrive in a specific, for example, teaching methods or strategies in teachings that we can use in order to teach chemistry to students.
Okay, right. Okay, this is very, very interesting, yeah, from the topic from Mr. Ecle. Okay, any question from the participant?
So we are actually touching three core areas, not just only on the content in chemistry, but of course in pedagogy
Pedagogy.
yes, sir, pedagogy,
Okay.
and
Yes.
on the use of technologies, these instruments in teaching students, specifically in laboratory.
Okay.
Okay, because we have also laboratories.
Mhm. So I'm also curious about your virtual laboratory. Do you make it by yourself or? I'm
Sir?
curious about your virtual laboratory, which you have demonstrated before. This is you developed by yourself?
It's actually, sir, from our university because we cannot really have the face-to-face or the actual
Yeah.
laboratory in order for these instruments. But I really, as an alternative, so our professors need to find similar laboratories that we can also get same data for this particular instrument, because I have also subject on instrumentation chemistry. That's why it's very hard for us. It's very difficult to carry to imagine
Yeah.
this. It's very difficult to imagine the these data or the information from the book, and you are going to put it in the actual setup. So if there's no laboratory, then we could barely know the working principles behind these instruments because of this pandemic.
Yeah, I think we have a same problem, sir. I think all of the world have a same problem about the practical, especially for us from engineering. Yeah, it's hard to make experimental. Yeah, yeah.
Yes,
That's
sir.
why all of the teacher all of the lecturer should be creative here
Yes,
to
sir.
make to make a design of the experimental method to our student like that.
Okay, but hopefully, sir, next semester we could have the face-to-face class, limited face-to-face classes, so that we could now conduct actual laboratory for specifically for instrumentations, because we could not really, even if it's virtual laboratory, because but you cannot really get to experience the actual instruments on how to properly conduct and demonstrate these spectroscopic methods, because it's really difficult to have it in reality than in virtual laboratory.
Yeah, exactly. Yeah, and also in Indonesia there is next semester also. It's already began for the class in the offline class. Yeah, it's limited. Yeah, but
Limited.
as you mentioned before, it's a better experience when we touch the instrument from by direct touch it, not by virtual, right? Like
Yes,
that.
sir.
Okay, I think there is no question. Is there any question for Mr. Ekla? We have 2 minutes more. Okay, I think that's all. That's enough, Mr. Ekle. Thank you very much for your present about the measurement analysis. You give us a new knowledge about measurement calibration in especially in chemical analysis. Yeah, this is a very very useful for us when we working in the company like oil and gas or analysis for the waste management in the industrial currently.
It
Okay, I
could also
think
be good, sir, if I could also discuss other spectroscopic instruments, but because we don't have that luxury of time,
yeah,
so maybe next time we
exactly,
could
yeah,
also,
because we don't have enough time.
yes, sir.
Yeah, maybe. next time you can come to Indonesia to visit us directly. It is my pleasure to visit you in our university here in ITS, in Surabaya. And
Yes, sir. It will be also
also,
my pleasure.
yeah, also next time I will wait for your invitation for from your university.
I will tell Ma'am Digamon,
Okay,
our
thank you very
international
much.
affairs director, sir, for that concern.
Okay, good. Thank you, Mr. Ecle, from your presentation. And I think our discussion is enough for today. I would like to appreciate what you share your knowledge to us. And that's for us, this is the new one for the measurement and calibration. Okay, thank you. Now I will back to my MC, Mr.
Thank you so
Asar.
much also, sir,
Okay, yeah.
for having me here. It's a very great opportunity also in my part to share what I have learned during my PhD here in the Philippines.
Yeah, exactly. I hope next year I would like to continue my PhD also, sir.
Hello, sir.
Okay. I hope next year I
Hello.
will continue my PhD also, sir.
Okay,
I
sir.
hope, could you hear my voice?
Yes, sir. Yes, sir.
Yeah, I hope next year I can continue my PhD also. Yeah,
That would be
okay.
great, sir.
Okay, thank you. And then I will back to Mr. Asar as the MC.
Okay, thank you, Mr. Putu, for being moderator in here. At the first, I would say once again I would say thanks to Mr. Kier for giving some knowledge and spend the time in this webinar. I hope your knowledge will be useful for us in future, Mr. And I think your material in this webinar is very interesting. Okay, in here I will remind to all the participants to fill the attendance and feedback link. Maybe the operator can share the attendance and feedback link in the chat Zoom meeting. Okay, finally, it is the last session from this webinar. I hope this webinar can be useful for us. I am as a master of ceremony would say from the tip of my heart to apologize for my mistake while presenting this event. Thanks to all the participants who have joined this webinar, our speaker, our lecturer, and the committee who have made this webinar run friendly. Thanks for your attention and see you in the next event from International Lecture Series of Instrumentation Engineering. Wassalamualaikum warahmatullahi wabarakatuh.
Okay, maybe before we leave, we can take a photo with Mr. Ecle together. For the operator, could you take a photo for all participants and also with Mr. Ecle for the documentation? Okay. Please turn on your camera. Okay. For the first slide. 1, 2, 3. Okay. Next one. Next slide. The second slide. 1, 2, 3. And the next slide. 1, 2, 3. Okay. Okay. I think it's all enough. Okay, I think it's all enough. Already enough. Thank you, Mr. Ecle, for your time. I hope see you.
Thank you
See you
also,
in
sir.
Philippines. Yeah?
Thank you. Thank you, everyone. I hope I will also see you next webinar series
Yeah.
that your college will be having.
Okay. Thank you, Mr. Ecle. Have a good and have a nice weekend for you there.
Thank you, sir. Have a nice weekend also.
Yeah.
Goodbye, everyone.
Goodbye, Mr. Clay. Thank you, Mr.
Thank you.